Welcome to the course. The topic of this lecture is TCP/IP protocol stack. In this lecture, we shall be discuss about TCP/IP protocol stack, basic functions of TCP, UDP and IP, and data encapsulation. So, start with introduction of TCP/IP protocol stack. TCP/IP is the most fundamental protocol in the internet, known as TCP/IP because the foundation protocols in the suite are the Transmission Control Protocol (TCP) and the Internet Protocol (IP). Just imagine, what is Internet? Internet is network of networks. There are so many networks all connected together. Inside a network, there are so many protocols, but somehow they all are able to communicate with each other. So there must be some common language which all these computers are speaking, and this common language is TCP/IP. So if a node means computer understand this TCP/IP language, then it can be communicate with any of the other computer connected in the internet. So TCP/IP allows computer to communicate or share resources over the internet. It is universal standard in the internet. It is used to bridge the gap between various different platforms. When you can think of different platforms, you can have different operating systems like Windows, Linux, Mac. You can also have different networks like Ethernet, ATM, and many more in LAN. In WAN also, there are different standards. So, how these different non-compatible platforms are work together? Answer is TCP/IP. TCP/IP is work as a glue to bind these platforms together. As you have seen 7-layer OSI model in previous lecture. TCP/IP also follows same layering structure but in some simplified manner. It does not contain all the 7 layers of OSI model. In fact, it contains a simplified 4-layer model. This slide shows TCP/IP model, the 4 layers of TCP/IP model. In TCP/IP model, the upper 3 layers of OSI model, application layer, presentation layer and session layer, is integrated in a single application layer. You can see it depends on the application whether you actually require a session, whether you need to do any changes in data presentation. So it depends on application. Instead of keeping different layers, TCP/IP integrated all these layers into a single layer. Next one is transport layer. This transport layer is more or less correspondence to OSI transport layer. This is responsible for end-to-end message transfer. Next is network layer. Network layer is also correspondence to OSI network layer. It is responsible for packet delivery across the network. And again, the data link and physical layer of OSI model are merged together in a single data link layer. This data link layer of TCP/IP model is somewhere called physical layer. So both the terms are used interchangeably for the very first layer of TCP/IP model. This data link layer is used for frame transmission over link. The point is, whenever you want to connect over internet, you want a network interface card. And network interface card integrated both the physical and data link layer. So this is the 4 layers of simplified TCP/IP model. This slide shows how data flows in the TCP/IP model. Data flow in the TCP/IP is again simplified. Node A is sender and node C is destination node and node B is intermediate node. Node A generates some data on application layer and sends it down to the transport layer. And transport layer sends it down to the network layer and it sends the data to data link layer. Data link layer sends it to the intermediate node and goes up to the network layer. And network layer decides where to forward the packet, means on which link. When it reaches to destination, it flows in reverse direction. A and C are communicating in this way. Same as OSI model, application and transport layer are not visualized over intermediate nodes. Now talking about TCP/IP protocol suite. TCP/IP protocol is not a single protocol, but it is a collection or family of protocols. And all these protocols are based on datagram approach. Datagram approach is already discussed in previous lectures. Like each datagram transmits independently, the message is broken up into several packets and each packet may follow different routes to reach the destination. Data sent from one node to another node as a sequence of datagram, not a message. Delay may be variable and arrival of datagram may also variable. These things were already discussed in the lecture. Okay. This diagram shows some of the family members of TCP/IP. They are more. Starting from lowest layer, data link and hardware layer. Sometimes it is called physical layer. Here it uses Ethernet technology, so you can also call it Ethernet layer. Next layer is network layer. The most important protocol in this layer is Internet Protocol, which we generally termed as IP. IP is responsible for routing of packets. In this layer, there are some other protocol also which we briefly describe in next slide. ICMP, IGMP, ARP and RARP. The next layer is transport layer. The two alternate protocol on the transport layer are Transmission Control Protocol TCP and User Datagram Protocol UDP. And at the topmost layer, application layer, you can be run any arbitrary user applications. There are some specific application also included in this family like File Transfer Protocol FTP, Trivial File Transfer Protocol TFTP, Simple Mail Transfer Protocol SMTP, Simple Network Management Protocol SNMP and Domain Name Service DNS. Here we briefly talking about some of the protocols of TCP/IP family members. First one is Address Resolution Protocol ARP. It is used to convert IP addresses to MAC addresses. As you all know, every computer which is connected over internet has a logical IP address. And already said, MAC address is physical address and it is also called hardware address of the device which is mentioned over NIC card. Next is RARP, Reverse Address Resolution Protocol, which converts MAC addresses to IP addresses. When data is flowing over network, these two protocols are very helpful. Next is Internet Control Message Protocol ICMP. It is mostly used for a device to send error messages to others. Next is Internet Group Management Protocol, IGMP. In this protocol, a node can send its multicast group membership to adjacent routers. Now, the next service is domain name system, which we used at application layer. DNS is basically a server which translates web addresses or URL like www.google.com into their corresponding IP addresses. So we don't have to remember all the IP addresses of each and every website. There is a command nslookup gives you the IP address of the domain you are looking for. This also provides the information of our DNS server. Here, this snapshot shows the nslookup command, which gives the IP address of the www.google.com. Now, let's talk about IP. What does IP do? Actually, IP is responsible for routing of packets from source to destination. It decides which node to forward the packet, then next node again decide where to forward the packet. This way packet will reach the destination. So the IP layer is responsible for routing. IP layer also has some additional features, like if it finds a packet is too large to forward the next node, it again breaks the packet into smaller packets. This process is called as fragmentation. IP uses datagram, and already discussed datagram is an unreliable service. Unreliable in the sense some packets may lost during transit, delivered out of order at the destination, and duplicate packets generated. Now, what does TCP do? TCP understand that IP that is below is not reliable. It knows maybe some packets are lost, some duplicate packets may be there, and packets delivered out of order. TCP tries to make the network connection reliable, taking some additional responsibility. How? TCP will explicitly check that the data that has sent is being correctly sent to the destination, because the destination will be sending back an acknowledgement at the transport layer to know whether it is received correctly or not. If it is not received correctly, it will transmit again, so that some reliability is maintained. So TCP tries to provide a connection-oriented reliable service. Reliable in this context means if some packet gets lost, it will resend. Here, the application has illusion that there will be some connection-oriented transmission at the transport layer, means virtual circuit establishment is there because the packets are received in order. Packets are received in order because acknowledgement are received from the destination end at the transport layer. That's why called transport layer, or TCP provides host to host reliable delivery of packets. So TCP done splits a message into packets, reassembles packets at destinations, retransmit packets that were lost in transit, It forwarded each packet to IP for delivery. And also, if any error is happening in packets, it will be done by TCP, not by IP. Now we talk about UDP. User Datagram Protocol UDP is the other protocol of the transport layer. It is somehow equivalent to IP, just a little extra thing beyond the IP. UDP does not provide any reliable kind of connection. So, what UDP does is, UDP provides connectionless, unreliable service for sending datagrams or packets. Here, it is using datagram service just like IP. It just provides transport layer interface to directly interface with IP. It does not provide any reliability like TCP. It does not order the packets like TCP. It simply receives the packet as it comes. There are some applications where if the packet gets lost, it doesn't care. Like some network devices periodically send some informative packets to central server to tell that I am good, I am good, I am good. So if some of these packets get lost, it is not matter because after some seconds it will come again. So there are some applications where reliability is not important. There we can use UDP because it is simpler than TCP and it is also faster than TCP. UDP header contains little information and it does not take care of any error. This slide is showing a typical scenario of computer network. Different user processes are at application layer. Next is transport layer, which uses either TCP or UDP. Already discussed, applications which requires reliability uses TCP and which does not require reliability uses UDP. Next layer is network layer, which only uses IP protocol for routing of packets. And the lowest layer is data link and hardware layer. In this simplified network, you can see there are several addresses coming in picture. In the lowest layer, commonly used network in LAN is Ethernet network. In Ethernet, something is Ethernet card. Ethernet card which you have plugged in your computer, in your laptop. In Ethernet, there is concept of Ethernet address, which is a 48-bit address, also called as MAC address or physical address. This MAC address is unique. So each Ethernet card in the world has unique 48-bit address. At the network layer, you have something called IP address, Internet Protocol address, which is 32-bit address that identifies, suppose, unique address of the network interface. Whenever you connect a computer in a network, that network interface will be having an IP address associated with it, and that IP address is also supposed to be unique. Now, a number of applications and user processes are using network. Now, how to distinguish which user process is sending data and which user process is receiving data? So, there is a concept of port number or port address. Port address uniquely identifies an application or user process running on device. Therefore, whenever a process sends a data packet, the corresponding port number is carrying with the packet, and whenever packets come back, there is a destination port number. The destination port number tells where to forward the packet. There are many programs are running. Which program to forward the packet? So, port address is uniquely identifies user process. IP addresses uniquely identifies network interface, and MAC address or physical address is uniquely identifies network interface card. Okay. Now, the next concept is encapsulation. You have seen in network protocol stack, data is sending in one direction and receiving in another direction. At the time of transmission of data, as data flows down, headers and sometimes trailers are added to the packet. We already discussed headers and trailers are contained relevant information about data packet transmission. And at the other side, when the data moves up, headers and trailers are removed. Here I am taking a simple example of trivial file transfer protocol TFTP to explain encapsulation. There is a TFTP client who is trying to send 200 bytes of data to a TFTP server. For TFTP protocol, the header size is of 4 bytes. You can see in this figure how TFTP client send data which goes down at client end and comes up at server end. Now you can see here the data is of 200 byte. When it comes up at TFTP application layer adds 4 bytes of application header. So this is the data which is TFTP generated. It sends it down to transport layer. TFTP uses UDP, not TCP. That's why UDP packet generated. So at this layer, 8 bytes of UDP header gets added. Then it comes to the IP layer. Here 20 bytes of IP header gets added. Now it's come to the Ethernet layer. In Ethernet layer, 14 bytes of header and 4 bytes of trailer gets added. In network, this is the whole data which is get transmitted. Actually, 200 plus 4 plus 4 plus 8 plus 20 plus 14 is equals to 250 bytes of data gets transmitted. Actually, we are transmitting only 200 bytes of data, and these 50 bytes are overhead. So the idea of encapsulation is when data is sending something, header gets added for transmission, and when receives data, header and trailers are removed. At the receiving end, at Ethernet layer, Ethernet header and trailers gets removed. When it goes up at network layer, IP headers get removed. Then at transport layer, UDP header gets removed. And last at application layer, application header gets removed. And you finally get only 200 bytes of data. So this is the whole idea about encapsulation. In this lecture, we talked about TCP/IP protocol stack. We shall be continue our lecture with TCP/IP in next lecture. Thank you.